Hello and welcome. My name is Torbjörn Nordling and I'm an assistant professor in automatic control at the Department of Mechanical Engineering at the National Shenggong University in Tainan, Taiwan. I'm also the general chair of this workshop. Now, behind me I have Tai Chi Single Whip, a piece of art created by Zhu Ming. It expresses how two dancers are dancing against each other. Now it's my great pleasure to introduce our honorary chair, Chair Professor Wu, for his welcome address.
It is a pleasure to welcome all of you on behalf of the National Shenggong University in Taiwan. I'm proud that our team, the NCKU Parkinson's Disease Quantifiers, are one of the finalists in the OpenCV AI competition. They are also arranging this workshop. Now let us all learn computer vision and AI using the OAK-D camera together.
Hello and welcome. I am Esteban Roman, a PhD student here at the National Shenggong University in Taiwan in the Mechanical Engineering Department and one of the speaker coordinators for this workshop. It is my honor to introduce Pierre-Nicolas Tiffreau, who is a computer vision engineer graduated from INP ENSEEIHT, Toulouse, France. There he studied various domains across signal and image processing, optimization, and machine learning. He will present Model is Trained, What's Next? Road to Machine Learning in Production. During his talk, you're going to learn the tools and techniques needed to avoid the pitfalls when deploying models in production while handling a complete production pipeline, and how to implement them with a computer vision use case.
Hello everyone, I'm happy to be here with you and I hope that you are as excited as I am for today's topic. First of all, I'd like to thank Nordling Lab for giving me the opportunity to give this talk today, and I suggest you attend all of the other talks during this week, as all the topics and people are just fascinating. What we're going to talk about changes a little bit from what is usually dealt with on those workshops, because we will not talk about edge computing or sensors too much, but on another facet of the AI field. We will approach the subject of production machine learning and MLOps, which is about managing all the different steps of the AI lifecycle efficiently, like DevOps has done for software development. For those who didn't have time to read the abstract of today's talk, we're going to remind it a bit right now. So, you all know that there has been an unprecedented rise of innovation and adoption in the field in the last few years, mainly driven by huge research labs and open source companies delivering so much to the world every year. But for companies using those new technologies, the facts are far from exciting. Indeed, it is said, and we observe it every day with our customers, that between 70 and 90% of AI projects never go further than the prototype stage and never see a production environment. Problem is, and I'm sure that you agree with me, that there is a lot of value to extract from correctly designed and managed AI projects. But if we don't go to production, all the efforts we put in trying to innovate when working on such projects are worthless. But don't worry, the goal of this talk is to show you the way of thinking required to put models in production and handle production pipelines the proper way. To do this, I will present some slides to you in order to introduce the different concepts of MLOps, show you some tools available on the market or in open source to apply those techniques to your project, and finally I will do a short hands-on creating a small production pipeline for a computer vision project. I hope you will learn cool things and that you will have the will to step up your game after this talk. I will be delighted to answer any question during the Q&A at the end of the presentation, but don't worry, you can still contact me after if I don't have time to answer you now. I just realized that I didn't present it myself. My name is Pierre-Nicolas. I graduated as a computer vision and machine learning engineer in Toulouse, France, where we started building Pixelia 2 years ago, which is an end-to-end AI development platform dedicated to computer vision with all the tools needed to handle the whole lifecycle of AI projects. Now, let's get back to our matters. We will start by redefining the AI lifecycle, but quickly, as I'm sure you're allowed to know it perfectly already. Then I will make a small side note on Datacentric AI. You will see how it will introduce the concept we will see later. Then, the most important part of the session, we will talk about MLOps, everything from the introduction through the different stages of MLOps maturity and all the tools and techniques to achieve your MLOps goal. As you all know, AI projects are made of three main parts: the training data, which must be stored, managed, cleaned, etc. This data is then used to train some machine learning models where we will iteratively do experiments in order to optimize the performance metrics. And finally, when we are happy with the result, we will deploy the model in production so the business application can use it, either on edge or from cloud sources. But once you're there, as the title of this talk suggests, it's not over, and all those steps are, in reality, integrated into each other, because a lot of things, notably the word, so the data, will change during the lifetime of the model. The focus on the model I talked just before led to this state that AI currently followed for many years. From the word of the renowned Andrew Ng, AI systems are composed of code plus data. Code being the model that is programmed using some frameworks in Python, C++, or R, etc. And the challenges for all the research labs around the world was to, for a given benchmark dataset such as the COCO dataset, create model architecture that would perform better and become state-of-the-art. This is called a Modelcentric Approach, keeping the data fixed and iterating over the model and its parameters to improve performances. Of course, that was amazing for us, ML engineers, to have access to always new and better model easily on GitHub and being able to experiment in order to create the best model for our project. For a lot of machine learning engineers, it gives us the feeling that after studying the ML theory so hard, we were finally applying this science package and trying to create something powerful. And that was good times, to be honest. The particularity of this period is that at the time, data collection was a one-off task, performed at the beginning of the project with maybe the goal to make the dataset grow with time, but with not much reflection about its inner quality. The deployments of the model created was usually at small scale. One server or device could handle all the load, and monitoring wasn't such a thing. But what was the biggest hurdle, which honestly was the main reason we started our company, was that everything was done by hand, from data cleaning, which is rather normal, to model training, validation, deployment, storage, sharing, etc. It was obvious that there was a problem and that some easy solution could be provided to handle such issues, but the solutions were either inexistent or too complicated to apply for the majority of organizations, such as huge ML platforms. But now the time has changed, and some influential people in the field, such as Dr. Andrew Ng, start proposing some new paradigm to deal with model optimization, this time by focusing more on the data part. This approach is now called Datacentric. You may have seen those words on a lot of startup websites, and it can have different meaning and applications. But I will start by introducing the concept. A data-centric approach is when you systematically change or enhance your datasets to improve the performances of the model, which means that contrary to the model-centric approach, this time the model is fixed and you only touch the data. Enhancing the dataset can take a lot of meaning, such as taking care of the consistency of the labels, finely sampling the training data, and choosing the batches wisely. Not always try to increase the dataset size. As an example of how models trained on benchmark datasets can be improved, a study showed that on average, 3.4% of the data in those datasets was mislabeled, which can take a lot of different forms. Imagine the increase of performance possible by just decrease this number to 0. But focusing that much on data, as it should continuously flow since we deploy models that can collect the data they are doing predictions on, means that you have automated all the processes behind the model lifecycle, from training through validation to deployment. This discipline is called MLOps for machine learning operations. Okay, we start to get to the heart of this presentation. You may already have heard some new buzzwords like AI ops, model ops, data ops, ML ops, but what does it all mean in the end? To me, one of the main trending topics with serious activities in the last 2 years is MLOps, which, as I said, means machine learning operations. If I try to give a concise description of what MLOps is, I think we can describe it as an engineering discipline that aims to unify machine learning systems development and deployment to streamline the delivery of high-performing models in production. So it's all about deploying models that brings value in the end, but we will see that doing this consistently with as much precision and coordination as we manage to in the software today with the establishment of DevOps is a really hard subject. But don't worry, today many companies put a lot of effort in simplifying those processes for you in order to help you mature your machine learning work in a durable way. By speaking about maturity, it has been established that there exist 3 levels of MLOps maturity. Level 0 is quite what we described until now, is all about building and deploying models manually for every steps and iterations. Level 1 is getting more interesting and is mostly about continuous training by automating the ML pipeline. And level 2 is kind of the grail when you are here. Your ML pipelines looks just like your code pipelines with DevOps practices with things like continuous integration and delivery. Now that we have introduced what MLOps is, I just wanted to recall what MLOps is not. Just 2 examples to illustrate this. MLOps is not about adapting existing non-production fitted tools to make them production ready, such as trying obscure ways to put Jupyter notebooks in production so data scientists can keep their ever way of work. I mean, notebooks are a really important and unavoidable tool when you start dealing with data science in general, but even if some companies like Netflix tells amazing stories about how their processes are notebook focused and how they manage their pipeline with notebooks in it, it's not for everyone, and they have put a lot of work to own their tools and platform so they can do so. So keep in mind that trying to productionize notebooks is globally a bad idea. Second one is monitoring. If you monitor a lot of things about your model, some you never look at, and most that are absolutely not related to your business key performance indicators, and you just check that your model is alive, there are so many important insights that you don't take advantage of. This is the act now, reflect never way of thinking, and it prevents you from going further into your MLOps journey. If you have other elements that come to your mind that can be considered as MLOps anti-patterns, I would be delighted if you share it with me and the community to elaborate this part. Let's start with the first level of MLOps maturity. Do not worry if you recognize yourself in some of those elements, it's totally normal and there are not a lot of people and companies worldwide that have attained the other levels. We're here today so you can reflect on those points and see how you can improve your machine learning game. As I said earlier, what defines this level the most is the manual way of doing everything in the so-called pipeline. The pattern I saw in many companies, even those where I started as an ML engineer, was that the business people came with a client problem or a brand new project that had to involve AI. So they handed the requirements to the data science team, and that has to work in its corner for a long time to find and clean data, and then spent weeks trying to optimize a model that reached a certain percentage of accuracy. But then what? Usually what happens is that the clients or the project has more complicated needs than those anticipated at the beginning, and because of the iterative test and learn nature of AI, everything has to be done again from the beginning. This is indeed not really in accordance with the agile practices that usually rules project and software development. One another characteristic of this level is that usually the models are deployed when they can be deployed, not when they should, which makes a huge difference in how they solve real-life business problems. Of course, the testing of machine learning script has always been way beyond the wine for software and is usually contained in the script, if any. Continuous deployment is almost never considered, or is considered unattainable, which is mostly because of the manual steps I was talking about, and because there is no large-scale, high-frequency deployment needs. And finally, the global ML system is rarely monitored or is monitored using anti-patterns like I said in the previous slide. To wrap up on this level, when you deploy ML models, the whole system can't and doesn't adapt to real-world changes as they occur. And sadly, the model often breaks. Here is the complete MLOps Flow according to the CD Foundation. You can refer to it to remind all the different steps of the pipeline. One interesting thing is the transversal parts that are data consistency and the workflow orchestration. Now that we have evolved a little bit and reached the level 1 of MLOps, let's see what characterizes our architecture that makes it different from the 0 level. Firstly, a large improvement is that our whole experiment pipeline has been automated, which means that no more resources are handled manually, experiments can be trained with an API call, everything is standardized, and all the artifacts created from runs are stored automatically. If you push this further, you even manage to automate hyperparameter tuning, which can make a huge difference in the exhaustivity of your scientific studies. Second important improvement, the models are automatically trained with new data as it arrived from the real world. Understand from the sensors, from your client, from API, whatever collect method you set up. Which means that you can be reassured to always be up to date. But this also means that data scientists and engineers must closely watch the model that are deployed and the data they are trained on, so the models doesn't shift in an unwanted way. To do this, and to be able to debug fastly, you must have some kind of similarities between your experiment environment and your production environment, which leads us to the next point. You have to use or create standardized and reusable components by using Docker containers, for example. Obviously, your models are now continuously delivered. They just have to be validated, but there is no more manual copy paste or download to deploy new models. So now, instead of maintaining the model only, you also have to maintain the whole pipeline, write tests, monitor, which is a really complex task and explains why only a few people manage to get all those steps straight. Good thing is that now our system can adapt to real-world continuous data, which allows us to maintain a one model pipeline properly. But working with a lot of pipelines for different clients, for example, would demand a lot of effort because the pipelines are operated manually. Which guides us to level 2, the Holy Grail, that really push the boundaries of the things we can do and the kind of system we are now able to operate. By that I mean large-scale, high-frequency systems. Now life is good, data scientists can now focus on analyzing data and becoming data-centric. They can also spend more time on testing new techniques, algorithms, and analysis. You have developed tools to package and containerize their code, so when they are done, the whole pipeline is automatically tested and deployed. This means that we have achieved fully automated continuous integration and delivery. The triggers of the pipeline renewal are multiple, as we monitor everything in a lot of ways at different stages. Every metric monitored can trigger the pipeline, or everything can be scheduled, it's your choice. The few manual steps that remains compulsory are the data and error analysis, to ensure that the training data and the models meets our high standards. So yes, you are data-centric now. Congrats. Well, at least in theory. Now, I'm going to show you some tools to help you progress in your path to the level 2, or at least level 1, of MLOps Maturity. What we are going to cover are some of the most important steps that comes to mind when we deal with MLOps. I've nearly presented them all in the previous slide, so you should not be surprised. Of course, the first step, one of the most important one, is the deployment, because it's the one that should finally solve your business case or project, at least in the beginning. Then comes monitoring. As I said, there is no MLOps without proper ways to monitor the underlying systems. After that, I will do a side note on Explainable AI, or XAI, where there are a few things to consider. And finally, all the different steps that characterize the different level of MLOps, the feedback loops, the continuous training, and the continuous delivery of model. I will be short on those last points because their implementation and how they are really achieved really depends on the company or project requirements, organization, teams, etc. Let's go down to deployment. For most of us, it's one of the most exciting time of the project when you can finally see your model in action, study its performances, but also pray that it never breaks. Here you can see a simple diagram of what I consider the bare minimum of configuration and packaging for deploying a model into production. Everything less complete than this can't be considered MLOps ready. But we are still going to see the different ways that you may or may not know that allows to deploy models and see how they compare to each other. Here are, in short, our options for deploying machine learning models in production. If you can make prediction using a web-connected system, there are a few options at your disposal. First one that you may, I know I did, have done is deploy a Flask server to handle the request and make the prediction. Second one, more advanced, is to use some complete and powerful engines such as Tensorflow Serving. And then the other part, I wrote a note on cloud provider services. Then a part that you might know better, as a lot of you are doing edge computing, is of course the best techniques to deploy a model on edge. I will not cover it, as the logic to integrate those options into a pipeline are not that different from the first one. I don't want to spend a lot of time on this, but for those who are new to the field, this shows you how easy it is to deploy a machine learning model on an API endpoint. There are plenty of articles on the web with tutorials showing you in depth how to do this, but here is a short working example of a model deployed on a Flask server. The key issues with this method is that it totally mixes the logic of the model and prediction with the API logic, which leads to more complicated stack traces and less clean code. API can be inconsistent. For example, you might have to change a route. You can create dynamic routing to new model version as you add it to the servers. And finally, it's an inefficient way, I would even say dangerous way, to manage your compute resources. Indeed, what if your model have to scale, but the web server does not? How can you decorrelate the needs for performances of both sides? How do you mitigate the costs of such a solution? It can only scale with pain. Let's move to a more robust approach of serving with, of course, a real serving engine, Tensorflow Serving. First, it solves our earlier problem of mixed logic, because it's a separate port. Even if it's more complicated than a Flask server, it is still quite easy, and spending time on it really worth it, I can tell. You can do batch predictions now, which means parallelizing your predictions. You have an API that doesn't change, as it is devoted to model management and prediction, and is quite standardized. Plus, you can use either a REST API or the gRPC API. For example, at Pixelia, we use gRPC as it improves performance and robustness of the API, but it comes with a bigger learning curve, so choose what is best for you. It natively supports different versions for the same model, which standardize the way API routes are written. But one of the major problems, and I'm sure that this is the question you're asking yourself now, if it's called Tensorflow Serving, can it only run TensorFlow? Well, in fact, yes. It does only run TensorFlow and Keras model for now, but some improvements are being made, and as we will see further, there exist some workarounds or alternatives. And I hope that it's not a problem for most of you, but I know that it can block some people. It only runs in Docker or Ubuntu. I'm sorry. Just for you to see how easy it is to run Tensorflow Serving and deploy a model, I took those screenshots. The first one showing you the minimal command to launch the serving engine, and the other so you can see what it looks like when correctly launched. Beautiful. Here I wrote a minimal example on how to make requests to the Tensorflow Serving server using gRPC protocol. We can tell that it's less intuitive than the Flask example, but it's not even that long, and I can guarantee you that this will give you a lot more confidence in your serving engine. Just to quickly wrap up on some resources that also allows to deploy models and that I encourage you to check. First, we have GraphPipe. That kind of solves the multi-framework model problems. Indeed, you can deploy TensorFlow models, and MXNet and PyTorch models can be converted to ONNX format, which can then be deployed to the same serving. It also comes with a lot of clients for different programming language, so it can be included in nearly any technical stack. Then is a mastodont of this game, MLOps Flow. If you haven't heard of it yet, it's a heavyweight solution based on Kubernetes that allows to orchestrate experiments, serving, and supporting pipelines at scale on any architecture in a good way. I will not cover it more here because I consider that even if it's very powerful, it can be complicated to take control of the solution and maintaining it properly. Then we have a solution called Simple Tensorflow Serving. I personally haven't used it yet, but it seems to support nearly all existing frameworks, including PyTorch and MXNet, and still seems quite easy to implement. I suggest you go check their documentation to make your own opinion. And if you have successful experience with simple TensorFlow Serving, I would be glad to hear it. Finally, we have cloud deployment solution like the cloud providers platform, AWS, GCP, Azure, and solution like ours, Pixelia. The great thing about those solutions is that everything is managed, maintained, and monitored for you, so they are really powerful tools. But they have to be compatible with your existing workflows, policies, and obviously comes with a price. For the price question, by the way, you are better going with a fully managed solution that can be expensive, but will really bring value if you have problems important enough. Whereas going with a fully custom solution hosted and maintained by you and your teams, which you may recruit for the occasion, often occurs high hidden costs and evolves slower than the cloud solutions. That said, let's go to our next chapter on the road to MLOps, monitoring. First of all, let's see the issues that can happen if you fail to monitor correctly or don't monitor at all your systems, inspired from real events. Imagine you run a recommendation system. At some point, due to the number of items and the popularity of some of them, your model can start drifting and predicting the same item to every customer for a long time before you even realize that there is a problem. Some fields where machine learning is applied are more regulated than others. Take the banking and insurance sectors, for example. If you allow credit based on a neural network decision and a regulating authority comes to audit your business, you must be able to explain how the system works and why it took one or another decision. If you fail to do this, I can guarantee you that the fines will be really high. Another kind of monitoring is to be reassured that what your model predicts, the reason why it has been developed, is still relevant to the business need and standards. If you don't, you will lose money, engagement, and many other things. But what exactly can or must be monitored in a machine learning system? I've been telling you that there really is a lot of things that to look up to since the beginning of this presentation. Let's see what it really means. One intuition that you might already have and that first justify the needs for monitoring and continuous training is the changes in the data distribution that your model makes predictions on. Indeed, the world evolves fast. Customer research changes, climate change, people start to wear masks in the street and your model has never seen it before, so it's now unable to detect people. This is all data distribution changes and your model must change with it. Must be retrained. What we tend to overlook, but can lead to huge problem, is the experiment production environment duality. This means that your model doesn't behave at all in production like it was during experimentation. One example is, imagine you train a neural network on images stored in a folder. When you open the file using OpenCV, it might not have the same data type than when you are trying to do predictions from your camera and your model doesn't detect anything. Model concept drift is the actual name to describe changes in data distribution that occurs during the lifecycle of the model. Adversarial attacks is difficult to track but can tell you when users are trying to fraud your models. Of course, you have to monitor the global health of the whole pipeline to be reassured that it can work with no downtime. And monitoring also helps you identifying edge cases that may occur in real world and wasn't part of your original training set. By adding those examples to your new training data and labeling them correctly, you will enhance your model in predicting for broader situations. The list of the things you can monitor is nearly endless. But remember our MLOps Maturity level? Let's see what needs to be monitored for each one of them. As we said, at ground level, the best you monitor is that your model is still alive and have decent performances, at least the one you had when you deployed. A simple dashboard reporting the usage and the latency of the model is sufficient to achieve this. At level 1, things start to get interesting. Of course, as the main component of this level is the continuous training, the most important asset to monitor is your CT pipeline health. For example, you can record execution time for each steps, checking that your database tables are always filled with the same information, etc. You have to be aware because machine learning systems tend to fail silently when they do. So you can't wait for it to throw an error to start investigating potential problems. To enable proper and business-related continuous training, you should monitor the following things that will trigger the pipeline. drifting, distribution changes, and edge cases. So you are sure that you always start to train a better model when the global performances start to decay. Having a continuous training pipeline incurs cost, a lot of cost, that can be exponential if you don't pay attention to what triggers your pipeline, how frequently it is triggered, is it always necessary, etc. I will not go in depth in monitoring specific for level 2 because the concept it offers are still out of bound for the context of this presentation, but you can imagine that as it introduces continuous integration and delivery into the pipeline, those processes needs to be monitored too, just like our continuous training pipeline from level 1. Here are some tools that will help you achieve monitoring depending on your level and requirements. First, there are 2 commercial tools that are pure ML observability and monitoring platforms. Then we have some open source tools that comes alone or in a complete stack that allows you to cover all the scopes you need to monitor. For example, Prometheus with Grafana and the ELK stack are pure dashboards and logging system. ELK also allows you for querying efficiently through your logs with Elasticsearch. Evidently is an open source tool dedicated to ML observability, but maybe will not shoot the same usage as Prometheus or ELK. You have to test some solution and see what is the best for you. I told you earlier about Explainable AI, saying that in some case it's good not to have a black box and be able to clearly understand and explain our model's prediction. Here are some tools that implement and wrap the mathematical intuitions behind explainability. We saw that level 1 of MLOps Maturity is mainly about continuous training, where the first part is called the feedback loop, because you use prediction of your models to complete your training data and start back the loop of the project lifecycle. To do this, you must rely on a machine learning platform that comes with a complete APIs you can communicate with. You can develop your own, but there are a lot of good existing solutions already on the market. A good feedback loop will have to trigger some alerts to the labeling and data science teams when new data has been coming from the model, so they can validate it quickly and use it for retraining. From this, you will be able to launch new training and tuning more efficiently based on some heuristic or thresholds triggered by the availability of new data. Here are some platforms you can use that offer the feedback loop. They are often end-to-end machine learning platforms such as Allegro.ai, Supervisely, and Pixelia. Each one is more or less dedicated to a subfield of AI such as pure machine learning, computer vision, NLP, etc. As I said, the feedback loop is only the first step of continuous training, and if you're at this step, you should complete your workflow with a full continuous training pipeline that will orchestrate all the training processes. But in addition to helping you automate the process, continuous training tool will also help you organize all your assets, artifacts, model version, data, etc. So you can always roll back to a previous state of your project, and you are able to see exactly what experiments and changes led to the current version of the deployed model. Here, we can find some good orchestration and experiment tracking platforms such as Weight and Biases, Neptune, MLFlow, and Pixelia. The final step to achieve level 2 is continuous delivery. Now you can go further into automations and deployments, and you can find tools that allows to perform shadow deployment, which means that your new model B will receive the same traffic as your model A without impacting the global response, but will tell you if your model would be good enough to be customer facing or not. You can also perform A/B testing, which is a bit different from shadow deployment because now both models are customer facing and they both receive traffic and make predictions. You can now analyze if one or the other is increasing your business KPI. You have access to some open source libraries to perform this, such as Seldon, deployed in MLflow, or Cortex, which allows you to deploy model and manage infrastructure on AWS EC2 clusters. And you have the Amazon all-in-one solution, which is SageMaker. And that's it. Thank you all for listening to my talk. I hope that it will allow you to get some insight on how to solve your actual and future problems when trying to deploy models while following MLOps good practices. Here are some resources that helped me build this presentation and that you can go check to go more in depth into certain aspect of it. Now, let's get to the practice. I will show you how to quickly build a continuous training pipeline for computer vision so you can see how everything I said actually looks like. Let's go. Alright, first we're going to see the architecture of the project we're going to do. So what we're going to program is the pipeline server that will simulate your project, for example. So it will take as an input some data that could come from sensors or an API or whatever that we will simulate in a notebook. It will also communicate with our serving engine, which will make the prediction and send the data back to our platform that will also trigger our pipeline server using webhooks. Let's go. Alright, so as I said, we're going to use Pixelia for this project. So it's an end-to-end AI platform we developed to support work on data, experimentation in projects, and also model deployment. So let's start by taking a look at our dataset for this computer vision project. So to keep things simple, I took a little version of a face mask detection dataset. I simplified it by setting the labels to a face detection. So as you can see, all the faces are annotated. We can go check how the annotation tool look like. Okay, everything has been annotated. We can see that labels are not very consistent. They do not take the whole face every time. So some work can be done on the data, but we'll see that later. So we are going to use this data set to train a face detection model. So it has 500 pictures. And let's see the project it is used in. So I created this little project called CV Workshop. So we can see that we have attached our data set. What we want to do now is to train a model. So I already trained one using what we call scans. So scans is our experiment tracking system that allows us to automatically create some experiments using distribution for hyperparameters. And using a training script that is normalized for all our experiments. So we can see it here. I will not enter into the details as it is a special Pixelia training script. So here, as you can see, we have trained 10 different models in 10 experiments. What we tried to optimize is the total loss of our model. Up, we can see that our best performer is the 8th one. So we're going to check on it. So this is the experiment dashboard. We can see here the evaluation metrics and some important data about how the training has gone. So training and testing splits, some logs about the loss, localization, classification, and what interests us, the total loss. All right. So in Pixelia, when you're happy with your experiment, you can export it as a model. So it will create a model that will be stored here. So here are all the train model we have. So this one, I called it face detector. All right. And if we take a closer look, as I deployed it, I now have a pipeline that has been deployed for my project with this model. And here is the URL for the API to make prediction on it. So for now, that's all for Pixelia. Let's get to the pipeline. So for the sake of this project, so our pipeline is a little web framework that will simulate your application. I chose to write it in Falcon, which is a web Python micro framework similar to Flask, but I prefer Falcon because it's faster and it's also, I prefer the way it's written. So, well, it's a basic web server. We have some resources that corresponds to the functions between our API's route. So here, this one is to handle the inference task. So we send it some images and it sends it to the serving. And we have some listeners that we will see later that allows us to connect to the platform with webhooks. So it will receive some webhooks from Pixelia. And here you can see we define our routes, the URIs, and just launch the server. In order to make my server, my little web Falcon server available to the world, I have to create a local tunnel on my machine so it can communicate with the real world through a public URL. So I'm just going to expose the same port as my Falcon server, which is 8002, and it will give me this up. Okay, let's do it again. Okay, now we have a public URL. I'm going to copy it and going to my organization settings. All right, I'm going to put it here and this is the root for our webhooks. Okay, I will keep all events since I don't want to choose only the one that interests us for now. Okay, so now Pixelia is set up. We have a local tunnel, so our little Falcon server can communicate with the world. Now we are going to talk about the data source. So I made this little notebook where we will just enter the same URL. So it will simulate the input data we want. So it will just capture a frame from my webcam and it will send it to our Falcon server on the infer resource, which will then send it to the serving and respond with the prediction from the model. So we can test it right away. All right, as we can see, we printed the prediction that comes to our Falcon server. So this is what the serving responds. So there are a lot of modeling boxes with the confidence score and the labels. All right, and if we go to Pixelia, we can see that, let's go to our dataset. We have one new picture, which is me, basically. Okay, so the prediction is not really good, as I used for the sake of this tutorial. Not so well performing model, so we have to refine the annotation up by just dragging it to my face. All right, let's get back to the data set. So what I'm going to do is I'm going to simulate the add of a few images to make our training data bigger. All right, we are going to do this 5 times. All right, so I sent 5 new images that I got predictions for that has been sent back to Pixelia. As we can see here, so we can, along with the file, so the file is the image, along with the file we can give some arguments to our serving that tells this to that told him to send the data back to Pixelia, which precise the name of the dataset that comes from our config file here. So we can see that this is our dataset. Send the prediction along with the image and also the threshold from which the prediction should be sent. So here I put it very low as our model is not so well performing. If you want to know more about all of these things about Pixelia, we didn't have time to cover it here, but you can check the documentation. So if we go back to our dataset, I will refresh the page. All right, we can see that we have all the new images here. I'm going to refine them to my face. All right. So I'm going to do this 5 times and be back. All right. So I refined all the annotations, so the bounding box are now closer to my face. So when you're doing image annotation, one important step is to review the images. So you will tell if you accept or if you reject the annotation. So you know if some images need a further attention from labelers or data scientists. So for the 500 first picture, I accepted all the annotation. Now I'm going to accept all of mine, and this is what is going to trigger the webhook from our Falcon server. So if we go there, we can see that we have a resource is for image reviewed that will listen to this event. So when I review an image, it will tell the server how much image remaining has to be reviewed, and if it the number of image is sufficient, so we want to retrain our model, we are going to launch an asynchronous task here using Celery that will launch the retraining of the model, that will launch a scan as I did the first time. So if we go there, I will accept the image. Let's get back to our server. Okay, we can see that my hooks endpoint got a post request. And if we go to Celery, so the asynchronous worker, we can see that it triggered the retrain task. So what is done here is we get our project. So everything, as I said, is in the config file with the project token and project name. So we know what we want to access. So it gets all the information from the config file. We then get the project. We want the information of what model is actually deployed. Then we will create a new scan. So as we saw earlier, this is the hyperparameter tuning task. We will call it workshop with Unix timestamp to make it different from each other. The configuration of it, so you can see the documentation, but what we want is to launch it on a remote server. So we have servers equipped with GPUs, and we will launch 5 parallel training. We will only launch 5 in order to not make this too long. Optuna is a framework that allows us to automatically create hyperparameters using some distributions that are here, as you can see, for the batch size, the learning rate, decay factor, decay step. So these are all the hyperparameters our script needs to train. And finally, it will launch this script that we have here, which is the script needed to train the model. So it uses our package Pixelia TF2, which is made for TensorFlow 2 models. And the model we want to use is, as I said, the one that was previously used. If we go back to Pixelia, we can see that the model that has been used was an SSD MobileNet V2 640 FPN Lite. So we will use the same model for the new training. So as I said, the webhook triggered the retraining task. So if we refresh this page, we can see that we have a new scan created here with a new timestamp, and that all the experiments are actually running. So I will be back when they are all finished training, and we will see what's next. Okay, it's been a few minutes now, and all our training runs has finished. So as we can see here, every run has succeeded. We have the loss information, the final loss information for every experiment here. We can see that if you want, you have the parameter importance for those experiments. We can see also a top performer, which is the 0, the first experiment. So let's check this. So as I said earlier, we have all our metrics. We have our loss, every logs. It's okay. But what is important is that when we launch a scan, each time a run ends, it sends a webhook to our little Falcon server to tell him to check if it's good enough to be deployed. So if we go check our server, we can see that we have received some triggers from the platform, and that those triggers should have triggered the deployment task. And as we can see here, it has been redeployed successfully. So this means that if we go back to our project, we have automatically deployed to the same endpoint. So we have a consistent API endpoint. We have redeployed automatically after the end of our training and the selection of the best model, our model to the serving. And if we want, we can predict on some new images with our new model, just like before, with the same API as we did. And we should see new images in our dataset. All right, here it is. So as we can see, the predictions are not totally all right, but for the sake of test, it will be sufficient. Thank you all for listening to this workshop. I hope that my English was correct and that you understand a few things about MLOps. Don't worry, the whole project will be available on GitHub, so you will be able to find all the architecture for the pipeline server. If you want to know more about Pixelia or MLOps, don't hesitate to ask questions during the Q&A session or send me a message on LinkedIn or by email. And see you later.
Hello, Mr. Tiffreau. Thank you very much for the great talk. I'm the host of today's Q&A session. We have put the link of our Google Meet in the chat, so if audience want to join us, please feel free to click it. At the same time, let me read out the question in the chat for you.
Yes, thanks. Nice to meet you.
So there are a few questions in Twitch chat. The first question is, what is your opinion of building MLOps in academic lab? Which part of the pipeline you think is the most important for a lab?
So for the first question, I think that it could be interesting to build some kind of MLOps pipeline in academic lab, but as the final mission is not as critical in terms of performances and uptime than in the industry, not every step of what I presented before should be taken in account. For example, I think that a continuous training and feedback loop are the most important things, and maybe have your hands on monitoring. So when you want to share your work with industry in later time, you can do it in great conditions.
Thank you very much. Next question is, thank you so much. It's very interesting talk. Could you roughly estimate what is the cost for level 0 company build out a pipeline and be at least level 1 company?
So as we saw in the hands-on, the test project I did during this presentation, I think that the easiest way for going from level 0 to level 1 is to have access or buy a license of already existing ML platform that allows you to quickly prototype and use your product in production, and then create your pipeline by hand, as we did, so you can mitigate the cost. It doesn't cost too much to you, and with some other open source tool in addition to the ML platform, you could achieve level 1 of MLOps, in my opinion.
Thank you. There are also 2 questions in YouTube chat. The first one is, thank you for your speech. It gave me a clear overview of the MLOps field. I'm curious about the monitoring. How do you monitor the training process?
So I don't show it during the hands-on, but during the training, we get all the logs, the telemetry of the training. So what happened in the terminals of the machine, the remote server. We get all the logs live in the platform, so we can monitor the advancement and the progression of the training epochs by epochs. So that helps you to monitor all the processes and that you don't have errors. And in the end, to control that the training has gone all right, you can check that you have your files that have been stored, such as the saved model, the checkpoints, the config file, and also that all your metrics and logs has been stored correctly, and that they meet your expectation in terms of performances.
Next question is for the last one. So if any audience want to ask more questions, please feel free to put in the chat. This question is follow previous one. It is, what criteria will be applied to monitor or to estimate the training of the machine?
So I assume that this question means that how you can tell if a training or a model from a training has been good enough or not. It's mostly due to performance metrics. So you can check for the loss, you can check for the IOU, the MAP. There are a lot of things that you can check for in performance metrics, but you can also perform evaluation. So controlling that your models perform well against your training data. So you can identify edge cases and select the model that either has the less edge cases or perform best against your training data.
Thank you very much. We still have a few minutes, so maybe we can just wait a few seconds if any audience want to ask more questions. And just for information for audience, we will have another workshop tomorrow 10 a.m. So please feel free to join us. Okay, since there's no question, there's no new question here. So I think this is the end of today's workshop. Thank you so much for the answer, and thank you so much for joining us. For more information, please check our website. We have also put the link in the chat. Look forward to seeing all of you. Thank you, everyone. Thank you very much, Mr. Tiffreau.
Yeah, thank you for having me.
Yeah, see you. Bye.
Goodbye.